Hi, I'm Zhenjia from Columbia. In this video, we present 3D dynamic scene representation that simultaneously discovers, tracks, reconstructs objects on the fly, and predicts their dynamics under robot interactions. Given a depth observation of a scene with an action applied to the scene, the goal of the algorithm is to predict the object motion under the interaction. The object motion is encoded as a dense voxel-wise 3D scene flow. To enable this prediction, the network also infers a 3D amodal object instance mask, where the 3D volumetric mask encodes the object's complete 3D geometry. The network then warps the scene representation with the predicted scene flow to produce spatially aligned features for aggregation. In the next interaction step, the warped representation is combined with the new action and scene observation for predicting the next object motion. Our algorithm is tested on a real robot setup, where the robot executes a random push action in each step. 10 interactions are executed in each sequence. On the right, we show our network input observation and output scene representation and motion prediction. Here is DSR-net. It takes in-depth observation and action as input. The scene encoder encodes the input scene volume into a scene representation, which is then used to predict an amodal object instance mask. In parallel, the action encoder encodes the input action, and the motion predictor predicts object motion represented as SC3 transformations. The scene flow is computed by combining the instance mask and the transformations. The warped scene representation is used as history in the next step. In our evaluation, we want to test whether DSR-net is able to first accurately predict object motion under different robot interactions, second, aggregate the history and encode object permanence and continuity, and finally, improve the performance of downstream tasks. First, we will evaluate the motion prediction accuracy. We compare with SC3-net and SC3 post-net. The visualization indicates both baselines can only infer motion for visible surfaces, and SC3-net can only infer the object mask for the moving object. Here is the next state prediction after warping. Next, we want to check our model's ability to aggregate the history and encode object permanence and continuity. Object permanence is the understanding that objects continue to exist even if they disappear from view due to occlusion. In this experiment, we compare our model with following alternatives: single step that does not use any history, no op that does not use motion to warp the representation before aggregation. Here, green cup is pushed behind the can. Our model can predict the permanence of the green cup even if it cannot be observed. In this simulation case, the can is pushed and the static Rubik's cube is occluded. Both our model and the no-op model can handle this case since the history contains the information of static objects. In the next step, the Rubik's cube reappears and then is pushed to behind the can. Only our DSR-net can handle this dynamic occlusion case. No-op model fails due to the lack of historical motion. Object continuity means the representation can recognize individual object instances and track their identity over time. Here we want to check the object instance consistency across different steps, where consistent prediction is labeled as green and inconsistent prediction is labeled as red. Here we can see that the single-step model cannot really track the object identity. Here is a more challenging case with 4 visually indistinguishable objects in depth. The DSR-net can still track the identities of these objects even when the position of the cubes are swapped. This experiment proves that the continuity is inferred from history aggregation instead of visual appearance. Finally, we want to evaluate whether dynamic scene representation can improve the performance of downstream tasks. We apply a shooting-based MPC to generate a sequence of robot actions in order to push objects in the scene to match a target state. In each step, we sample a sequence of actions and choose the one with the lowest cost. In the second step, DSR-net correctly captures the occluded object and chooses the appropriate action, while SC3 post-net fails in the third step. The comparison indicates that the final state of our DSR-net is closer to the target state. Code and data are available online. Thank you for watching.